Hello gentlemen, welcome back. Purpose of this video is to continue studying zeros of polynomials, and we're going to look at a couple theorems right off the bat, and then we're going to do a couple examples. Okay, so let's get started. Let's look at the fundamental theorem of algebra. Basically it says if fx is a polynomial of degree n is greater than 0, then f has at least one 0 in the complex number system. And remember that the complex number system incorporates both imaginary numbers and real numbers. Okay, so let's make sure we remember this. This is both real and imaginary numbers. Okay, and we started looking at complex numbers last section, so hopefully you understand that, and we're going to see what we mean by having complex zeros. We can actually take this a little bit further, and we can talk about linear, look at this linear factorization theorem, and basically says that on the set of complex numbers, we're going to have exactly n linear factors for a polynomial. Okay, so if I have a polynomial of degree 4, I will have precisely 4 linear factors. Now these roots, or these zeros of the function, c1, c2, c sub n, those can be complex numbers. They're not all real numbers. They're not guaranteeing that we have real numbers. We're guaranteed that we have n complex zeros of any polynomial. Okay, so we have precisely n factors, linear factors. So if I have a polynomial of degree 5, I have 5 linear factors, whereas c1, c2, all the way up to c5 are in the complex number plane. They could be all reals, they could be imaginary. We're going to learn more about imaginary roots in a minute. Let's talk about the real roots. Okay, the rational zero test. If we have a polynomial, a sub n, x to the n, a sub n minus 1, x to the n minus 1, etc., etc., every rational zero has the form of p over q. Now, p are the factors of a sub 0, okay, and q are the factors of a sub n, right there, okay? So this is the rational zero test. So I can determine, if I have a fourth degree polynomial, I can figure out, what are the possible rational zeros that I'm going to have. All right, so this is going to come in handy as we try to find the linear factors and the zeros of a function. Easiest way to see this, fellas, is to do a couple examples. So let's do that now. Find all the rational zeros of the function. Okay, so if I'm looking at p over a q here, okay, p is going to be the factors of 6. Okay, so the factors of 6 we know are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So those are my factors of p. Q here is simple because q is only 1. And so knowing that, I can use the rational root zero test to determine that my possible roots are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, this p over q ratio. Okay, now my advice is to try to find one. I always start right here, plus or minus 1. If I plug in 1 here, I get 1 minus 7 minus 6. That's not going to work. But maybe if we plug in minus 1, we get negative 1 plus 7 minus 6. That actually works. So it's not hard to show that this is a 0. Once I have one 0, then I can use synthetic division to further factor. So let's do some synthetic division here. Again, I have a 0 here because there's no x squared term. Okay, so if we bring down the 1, we go through synthetic division. 1, negative 6, 6, 0. So we can see that it's a 0. And then I can factor this. Original function is x plus 1 times x squared minus x minus 6. Now this is just a quadratic. If I look carefully at this, I can see that I can factor that as x plus 1, x plus 2, and x minus 3. Okay, and again, so I'm asked for the rational zeros. I can see that the rational zeros here are going to be negative 1, negative 2, and 3. Okay, let's do another one. Now we have a fourth degree polynomial. Again, if we're looking at p over q, here in this particular example, p is equal to 20. I'm sorry, P isn't 25. When we're looking at this, I want the factors of 25. Okay, P is the factors of 25. So P here is going to be plus or minus 1, plus or minus 5, and plus or minus 25. Okay, Q is the factors of 2, plus or minus 1, and plus or minus 2. Okay, so I want to look at the ratio of P over Q, and I will get those are my possible factors. Okay, again, I would tell you to try to find one, and I found one. X equals 0 is one of the factors, and you should be able to verify that. We'll use synthetic division to do so and to simplify down. If I do synthetic division here, bring down the 2, negative 13, negative 13, 10, 10, 25, 25, 0. Okay, so now I can rewrite this. Remember, this is the coefficient of the x cubed because this was x to the 4th. I can write this as x minus 1. There's one root. 2x cubed minus 13x squared plus 10x plus 25. Okay, these coefficients are coming from right here. Now what we want to do is look at this particular problem right there. We want to try to factor that one a little bit further. Okay, and if I look here again, I still have the same factors, the same P, same Q. And again, close inspection, you can find that x equals negative 1 is also a 0. Again, finding one that works right off the bat makes it more simple, because then I can use synthetic division. If I use synthetic division here, bring the 2 down, negative 2, negative 15, 25, negative 25, 0. That allows me to factor even further. Okay. Now again, I have a quadratic here. All right. If I wanted to find the roots of that, I could either use the quadratic formula, or I can simply factor it. This is factorable. Get it right here. And now what I need to do is just set each one of these equal to 0. So x is 1, x is negative 1, x is 5/2, or x equals 5 are going to be all the zeros of that function. Okay. Now we can take that information and graph this function. Okay. Now I know the zeros. I know the maximum number of zeros I can have is 4. The maximum number of turning points is 3. Okay. I know I have an even degree, and so I should know what my end behavior is going to be. Okay. Leading coefficient is positive, so that tells me that my end behavior, both as I go to the left and the right, I'm going to finish like this. This is going to go off to infinity on both sides. Okay. I also want to make use of the fact that I have the zeros that we just found in the last problem. And let me just get rid of this here for you. Okay. And let's note a couple things. Here is 1 0, 2 zeros, 3, 4 zeros. My end behavior is going off to infinity on both sides. I have 1, 2, 3 turning points. Okay. I have a relative min, a relative max, and a relative min here. Okay. And I could find those on my calculator. I'm going from decreasing to increasing. I'm going from increasing to decreasing here. And then I'm going to go from decreasing to increasing on that side. Okay, so again, I can use my zeros to help me graph the function. Here's some practice. I want you to read section 2.5. Look at these examples in particular. A few problems finding zeros using the rational zero test or theorem. And the next video is going to do some more practice, basically just going to be examples, so that you get a little bit more seeing how we find the zeros, and then how to use them to help us do our graphing. Okay, so basically we looked at 3 theorems. We looked at the fundamental theorem of algebra. We looked at the linear factorization theorem, and then we looked at the rational zero theorem. Okay, so if you have any questions, fellas, make sure that you're emailing me, and you may want to even check out the next video before you start doing these problems, because it'll give you a little bit more, a few more examples before you start. Okay, have a good day, fellas.